All right, let's just dive right in. Imagine trying to precisely control a chaotic, boiling river of sticky molten plastic. And not just control it, but force it into microscopic layers and intricate shapes without a single tiny flaw. Sounds basically impossible, right? But everyday products, like those ultra-thin barrier films keeping your groceries fresh, or complex automotive parts, they rely entirely on us doing exactly that. So welcome to today's Explainer. We're going to explore how we actually tame that chaos. We'll see how we use the deep math of fluid mechanics to build what's essentially a virtual blueprint. Specifically, we're going to focus on how to analyze, evaluate, and actually apply computational fluid dynamics, or CFD, to completely revolutionize the design and manufacturing of polymer products.
Here's our blueprint for today. We're looking at the polymer processing challenge, measuring flow with rheometry, mathematical modeling and transport, applying CFD in manufacturing, real-world applications, and finally, the future of simulation.
All right, part 1, the polymer processing challenge. So the core industrial problem we're facing here is really all about physical control. Whether we're dissolving a polymer to apply a super thin coating or melting it down to force it into a mold, the journey is just incredibly demanding. Think about a standard injection molding setup. We have to take this highly viscous, ultra-sticky polymer from a reservoir, push it through a nozzle, down a sprue, split it into runners, and then force it through a tiny gate into a mold cavity. Oh, and we have to do this perfectly, every single time, without introducing any air bubbles or structural weaknesses. No pressure, right?
To actually master this chaotic journey from melt to mold, we really need 3 essential ingredients. First up is fluid mechanics. These are the fundamental rules governing how fluids move. Second is rheology. This lets us map the specific and honestly sometimes bizarre material properties of the plastics we're dealing with. And third, computational fluid dynamics, or CFD. CFD is where the magic happens. We take those rules and properties, throw them into a computer simulation, and actually design and optimize our manufacturing process before a single drop of plastic is ever melted.
Moving on to Section 2, measuring flow with rheometry.
Okay, so to understand how our polymers flows, we use a tool called a rheometer. It basically shears the material between 2 surfaces. But we have to make sure we're operating in the right physical regime by comparing the rheometer's gap to the shear wavelength of the material. Now, in the surface loading limit, the shear wave is completely damped out before it can cross the gap, kind of like a ripple just fading away in a massive lake. But for polymer melts and concentrated solutions, we always operate in the gap loading limit. Here, that shear wave propagates across the entire gap without damping. Imagine a wave bouncing perfectly between 2 close walls. This is absolutely crucial because it allows us to get accurate measurements of how the whole sample behaves.
And that brings us to the actual hardware. One of our absolute best tools is the cone and plate rheometer. You just place the polymer between a flat plate and this very shallow rotating cone. The sheer genius of this design is really twofold. First, it requires a tiny sample size. We're talking roughly just 1 gram. And second, because of the cone's specific geometry, it provides a highly uniform shear rate across the entire sample. That makes the math super clean and the data highly reliable.
Now let's contrast that cone and plate setup with the parallel disc rheometer. Here, the polymer sits between 2 flat discs. It still only needs about 1 gram of material, which is great, and it has one massive advantage. You can change the temperature really easily without having to reload the whole sample. But, there's always a catch. It has a major drawback. The shear rate isn't uniform. It actually varies from 0 at the center all the way to a maximum at the outer edge. So while it's fantastic for certain tests, it's just not ideal for those complex, nonlinear studies.
And honestly, we need all the help we can get because polymers are tricky. When we input mechanical energy to shear the sample, that energy has to go somewhere, right? It's often dissipated as heat. We call this viscous heating. In a sliding plate setup, for example, the maximum temperature literally spikes right in the middle of the fluid. So why does this matter? Well, because viscosity changes with temperature. The very act of moving the polymer generates heat, which then changes its viscosity mid-flow. It's a totally chaotic variable, and it perfectly illustrates exactly why we need such robust math and CFD to track what's actually happening in there.
Section 3. Mathematical modeling and transport.
So when we're modeling these systems, we generally break the motion down into 2 fundamental types of flow. On one side, we have poise-away flow. This is driven by a pressure difference. Just think of squeezing toothpaste out of a tube. On the other side is couette flow. This is a simple shear flow driven by a moving surface that drags the fluid along with it. Imagine dragging your flat hand across the surface of a swimming pool. In reality, though, our industrial processes are usually a really complex combination of both of these.
To actually build our CFD models, we have to start with the most basic rule of all, the conservation of mass. For flowing polymer melts, we just assume they're incompressible, which makes a volume balance perfectly equivalent to a mass balance. And that gives us the continuity equation. Picture an imaginary 3D wireframe suspended inside our flowing fluid. The continuity equation ensures mathematically that whatever volume of fluid enters that wireframe must perfectly equal the volume exiting it. It keeps our math grounded in reality.
Next up, we apply the concept of creeping flow. Look, when we're dealing with highly viscous polymer melts, things like gravity and the fluid's own momentum, its inertia, they hardly matter at all. The viscous forces completely run the show here. In fluid mechanics, we say this is a flow where the Reynolds number equals 1. Knowing that we're in creeping flow is a huge deal because it allows us to dramatically simplify those complex Navier-Stokes equations, tuning our math specifically for thick, molten plastics.
All right, Section 4, Applying CFD in Manufacturing.
Okay, so how do we know if our CFD software is actually working to build a true digital blueprint? Well, engineers run physical experiments to check. In studying down-channel velocity profiles inside a screw channel, researchers literally injected dye markers right into the flowing plastic and tracked their movement. And the amazing thing? The physical dye patterns flawlessly match the velocity profiles predicted by our numerical simulations. No way, right? But it proves that when we evaluate a design in CFD, we can fundamentally trust those results in the real world.
CFD also lets us map invisible forces, like pressure. Inside an extruder screw, our CFD models can show us exactly how pressure rapidly builds up in the tapered compression section of the helical screw. By analyzing this in the software, we know that this specific taper promotes really intense mixing, and that is absolutely critical when we're compounding materials together, like blending polypropylene with talc. We can safely test all these different screw designs digitally before anyone ever machines a single piece of steel.
Section 5. Real-world polymer applications. This brings us to one of my absolute favorite applications, co-extrusion. A 7-layer symmetrical packaging film is basically this microscopic sandwich of structural layers, adhesive tie layers, barrier layers, and recycled layers, all bound together. To create this, we use a really complex flat slit die. And let me tell you, you absolutely cannot design a metal die to flawlessly merge 7 separate, microscopic layers of molten plastic at high speeds just by trial and error. Analyzing and evaluating the flow via CFD is quite literally the only way this incredibly complex engineering becomes possible.
And those microscopic barrier layers I just mentioned, they're made of highly specialized polymers. EVOH, which is an ethylene vinyl alcohol copolymer, is an absolute fortress against oxygen. And PVDC, polyvinyl leading chloride, is incredible at stopping moisture vapor. But here's the thing, these materials are super difficult to process and they're expensive. CFD allows us to design equipment that spreads these polymers into layers thinner than a human hair. This lets us utilize their barrier properties efficiently, without wasting a drop of expensive material.
Here's another fantastic example, wire coating. Remember those 2 fundamental flows we talked about earlier? Well, in this process, molten polymer is pushed through a die under pressure. That's our Poiseuille flow. But simultaneously, the solid wire is being rapidly pulled through the center of that die, dragging the plastic right along with it. And that's our Couette flow. CFD lets us balance these 2 opposing forces perfectly, ensuring the wire comes out flawlessly centered and evenly coated every single time.
The application of these transport phenomena equations also allows us to scale up massively. Just behold a 4-head sheet co-extrusion line. You've got 4 separate extruders feeding different molten polymers into a central die block. It honestly resembles a giant mechanical octopus. But thanks to rigorous mathematical modeling, the behavior of those fluids inside those massive steel blocks is completely predictable.
And finally, just consider the sheer towering height of a high-output blown film line. The plastic is extruded upward in this continuous, incredibly thin, fragile bubble that stretches multiple stories high before it cools. This entire massive industrial operation completely depends on the precise, calculated rheology and perfectly tuned fluid dynamics happening right down at the very base of the machine.
Which brings us to our final section, the future of simulation.
We've seen how measuring rheology and applying things like the continuity equation in CFD allows us to design tools that actually tame the absolute chaos of molten polymers. By replacing physical trial and error with accurate digital blueprints, we've enabled wild technologies like microscopic 7-layer barrier films and those towering blown film lines. So, I'll leave you with this thought. As our processing power grows and our fluid dynamic models become even more precise, what current manufacturing impossibilities will CFD solve next? Keep that in mind the next time you pick up a seemingly simple plastic product. Thanks for exploring this explainer with me.